Now we start our study of using the normal curve to find probabilities. In a previous screencast, we spent time finding the area underneath the standard normal curve. And we did that with finding area to the left of a particular z-score, to the right of a particular z-score, and between two particular z-scores. Those areas we were finding represent probabilities. So when you find, for example, the area to the left of a particular z-score is 0.7, that's the same thing as saying there's a 70% chance of you getting a z-score lower than that particular z-score. Let's look at an example. So IQ distributes normally in the adult population. The Wechsler adult IQ test has population mean 100 and population standard deviation 15. Suppose one adult is chosen at random. What's the likelihood the person's IQ is between 85 and 115? So we visited this problem in a previous screencast, but now we're going to ask a particular probability question. Suppose you choose one adult at random. What's the chances that their IQ is between 85 and 115? Let's first get a sense of what's going on here pictorially. So we have IQ scores, they distribute normally. So you've got this bell curve, and we've got on our horizontal axis, we got our IQ scores. And right here, you have the mean, which we're told is 100. Right at the inflection point, here, this inflection point and this inflection point, that distance from the mean should be precisely the population standard deviation. So this corresponding IQ score right here should be 115, because that's 15 more than 100. And this IQ score corresponding with that inflection point should be 85, since 85 is 15 less than 100. We want to know, if you choose an adult at random, what's the likelihood that person's IQ will fall in this range here? Technically, we can already answer this question without learning anything new. This is one standard deviation to the left of the mean, and this is one standard deviation to the right of the mean. What area is between one standard deviation to the left and the right of the mean? Well, that was the empirical rule. If you can recall, the empirical rule says that 68% is within one standard deviation, 95% is within two standard deviations, and 99.7% is within 3 standard deviations. So we technically don't need to do any computations here. Within 1 standard deviation each way, we've got a total of 68%. So 68% of the area amounts to a probability of 68%, since the area is the probability. So if you take one person at random, the likelihood that their IQ falls between 85 and 115 is 68%. Let's try another problem using the Wechsler IQ test. Suppose one adult is chosen at random. What's the likelihood the person's IQ is above 105? Again, with the Wechsler IQ test, the population mean is 100, the population standard deviation is 15. And let's first pictorially get a sense of what's going on here. You don't absolutely need to draw a picture to see what's going on, but it can be really helpful and can help you avoid mistakes. So again, the Wechsler IQ test scores are distributed normally or along the bell curve. And right here, the mean is 100. Right here at this inflection point is 15 to the right, because 15 was the population standard deviation. And then 105, of course, is right about here. So we want to find the area above 105. So that means to the right of it. So we want to find this area. So if you look at this, hopefully you know that your answer needs to be less than 50%, because 50% is to the left of the mean, 50% is to the right of the mean, and this is less than that right-hand half. But notice now that the empirical rule does not help us. First of all, we're not precisely 1 standard deviation away to the left or the right. We're only 1/3 of a standard deviation to the right. And we're not talking about between, we're strictly talking about the area to the right, which technically this goes on out forever in that direction. So how are we going to do this? Well, technically, we already found the area to the right under the standard normal curve. And this is not the standard normal curve. Right now, these are raw data values x. However, if we convert the x values to z values, we can then use the standard normal distribution table to get the area to the right of that point. So you can see up here, this is our strategy for solving a problem like this. We take our raw data values, convert them to their z-scores, and then we can use the standard normal distribution table to find the corresponding probabilities or areas. So just as a reminder, I write P for probability here. These are the areas. They're the same thing. Probability equals the area. Let's first convert our raw score to a z-score. Again, this raw score right here was 105. To get the corresponding z-score, you may recall this formula from the first unit, that z is the difference between the raw data value and the population mean divided by the standard deviation. So we've got z equals our raw data value is 105 minus the population mean is 100, all divided by the population standard deviation, which is 15. The difference in the top is 5. We've got 5 over 15. And then in order to use our standard normal distribution table, we need to round our z-scores to the nearest hundredth position. So 5/15 is a third. Rounded to the nearest hundredth position is 0.33, because that's how accurate it is on our table. Ultimately, again, I don't actually need to draw this graph here, but to visualize what's going on, we just took this raw data set and we converted it to its standardized form. The z-score under the standard normal distribution corresponding with the mean is 0. And we are right here, right next to it, just like it was up here. We are right here at a z-score of 0.33. And we now want the area to the right of that. These two areas are the same, this one here and this one here. If we now turn to our standard normal distribution table, the area associated with the z-score 0.33 is 0.6293. Is 0.6293 the area to the right of this point right here, or this one down here, whether you're talking about the standardized or the raw form? No, this is less than 50%. We already discussed that this needs to be less than 50%, and you can't forget, when you read our table, this area is the area to the left. The number that's in the table is the area to the left. So that's this area over here. So to get the area to the right, we already saw that we need to do 1 minus the area to the left, and we get 0.3707. So when you choose one adult at random, the likelihood that they will have an IQ above 105 is 37.07%. Let's take a look at another example.